Problem 1713. In this particular circuit, we'll notice that both diodes D1 and D2 are forward biased. That's because the positive end of the battery is attached to the anode of D2, and the negative end of the battery is attached to the cathode of D1. So they're both forward biased. Notice also that the 9-volt supply is large enough to forward bias both diodes, each having a forward drop of 0.7 volts. So let's write Kirchhoff's voltage law around this loop and see if we can determine what the voltage drops are across the resistors. So current will flow in this direction, and that will create these polarities across the various components. It doesn't matter which way we walk around the circuit. I always like to start from here and walk around clockwise. So we'll write Kirchhoff's voltage law starting from here, walking around clockwise. So the first voltage we see is plus 9 volts. Plus 9 because we see the positive end of the battery first. Then we see minus voltage across R1. Then we see minus the voltage across the diode, which is 0.7 volts. Then we see minus the voltage across R2. And then we see minus another 0.7 volts. And that all adds up to 0. Now we can collect these voltages over here. And so we end up with 7.6 volts minus VR1 minus VR2 equals 0. And we can rearrange the terms so that we get the voltage across resistor 1 plus the voltage across resistor 2 is equal to 7.6 volts. Now the voltage across R1 is simply, using Ohm's law, the current in the circuit times the resistance. So we can write this expression as voltage on R1 is equal to the current, which we don't know, times the resistance, which is 100 ohms. And we can write the voltage across R2 as I1 times its resistance, 200 ohms. Now, we can make the substitution of these two expressions into this equation, and so we get I times 100 ohms plus I times 200 ohms is equal to 7.6 volts. And of course we can factor out the I, so it's I times now 300 ohms is equal to 7.6 volts. And we can calculate I as being 7.6 volts divided by the 300 ohms is equal to 25.333 milliamps. This tells us, therefore, that the voltage on R1 is equal to 25.333 milliamps times 100 ohms. And multiply that out, that's equal to 2.5333 volts. And likewise, the voltage across R2 is equal to the same current, 25.333 milliamps times 200 ohms is equal to 5.0667 volts. At this point, what we should do is check to make sure that we have got all of the correct answers. So the one way to do that is we can take all of these voltages here and put it back into our original equation, which is Kirchhoff's voltage law, which says that the sum of all these voltages has to equal 0. So let's just do that. So we're just going to do a check. And what we said was 9 volts minus the voltage on R1, which is 2.5333 volts, minus 0.7, minus the drop across R2, which is minus 5.0667, minus the drop across the second diode, equals, and if we add this all up, we'll discover that this impact is equal to 0, and therefore we have the correct solution.